get this video through this video and accomplish some bigger, better stuff. But I don't know. I guess we'll just have to see how we work on time. Guys, what I hope you got from the previous video is that we can take the chi-square method, which is a very simple statistical technique where we can examine the relationship between two categorical variables, and via a log transformation we can re-express the chi-square as a regression model. So in a nutshell, we can take chi-square and via some natural log transformation, we can take a look at this as a linear model, and that's going to play a huge role. Just a second. I'll tell you what, this thing's acting wacky on me again. I don't know why it keeps scrunching in, but I don't like it. Okay, guys, for our previous model, we examined the relationship between belief and political party, and our model turned out to be the following. I just want to write that, if nothing else, just for me. And this was that the natural log of the observed value was 5.52 plus 0.18 times the party plus 4.83 times the belief plus the natural log of our error. So guys, this would naturally lead into the natural log of the error being equal to the natural log of the observed component minus the natural log of the expected component. And guys, you'll see me from, and we talked about this back in 5500, that anytime at this level when we talk about just the log transformation, we're really implying the natural log transformation, or at least I am. So guys, if nothing else made sense from the previous videos, remember that really at the end of the day, all we learned is that the chi-square can be re-expressed as a linear model. Now, what do these betas mean? For example, that 4.83, how do we interpret that? Well, the interpretation of coefficients from a linear model have to do with kind of a variation around the mean, and in these models they just have they deal with kind of a variation around the expected frequencies instead. So keep that in mind. We're going to, my dog's going, that's actually not my dog, that's the neighbor's dog. So oh wow, this is crazy. Just got to laugh at it. All right, I'm not going to start over. So guys, generalizing the previous video where we wanted to examine the relationship between two, I should say, taking the previous video and generalizing. I'm sure you see where we're headed here. What I want to do is be able to examine the relationship between three or more. Those get really, really, really messy. Or more categorical variables. So, it shouldn't be really any surprise that that's where we're headed, because one thing I told you that was where we were headed in the previous video. So, so guys, keeping a simple procedure, expressing categorical data in the form of a linear model. Shoot, I'm gonna have to Google that. That's just driving me insane, and it's keeping me getting me off track too. Provided that we use the log transformation. So boys and girls, that's where we are headed. All right. And it's kind of cool stuff. Plus, I think it really sets a stage nicely for logistic regression. So guys, let's think about a 3 predictor model. Back when we were in the days of ANOVA, more specifically, when we had a factorial ANOVA. And let's say that we wanted to examine group means across 3 groups. And let's say that our groups were A, B, and C. What this would lead to is it would lead to 3 two-way interactions. Between AB, AC, and BC. And it would also lead to 1 three-way interaction which would clearly be A, B, C. So one way that we can think about this in the context of categorical variable is we can think about the observed, and let's think about it in the 3 variable example. So we're going to have ijk instead of ij. We can think about this first of all as our model, which would be in the form of b0 plus b1 times a sub I plus b2 times b sub j plus b3 times c sub k. Then we're going to come in with a coefficient for our first two-way interaction. Then we'll come in with another coefficient. So this will be what, ik? Plus another coefficient, we'll call this obviously B6 to look at BC JK. And then we're going to introduce the coefficient, in this case the B7, for the three-way interaction. And at the end we're going to have our error term that completes the relationship. Now, guys, by hand, these things get pretty ugly. But you know, again, following what we did before, we can take the natural log of the observed, which would be our model, plus the natural log of the error term. Now, something I think you probably found kind of strange, or you should have kind of found kind of strange in the previous previous illustration. We start talking about these saturated models, and when we had 2 categorical variables, we ended up getting the saturated model, which just said we had no error. And when we, I should say, we had no error when we included all the available terms. And when from here on out, when I talk about all the available terms, what I'm actually talking about are just the main effects and all the interaction effects. So when we include all these, we get no error. And think about that as your standard error. And this leads to what we call a saturated model. Now, I don't know about you, but to think that we just are able to explain things with no error, and it's kind of like if you take a sample from a population and you use it to generalize to your entire population, because of sampling variability, you're going to have a sampling error, a standard error. You know, but what if you were able to take every single observation in your population? well, there would be no generalization to be made because you've exhausted your entire population when you collected your data. Well, in statistics, we don't have those opportunities to work with an entire population. We typically are taking a sample and trying to generalize to some population. So what we end up with now is something that we didn't talk about this earlier. And when I say earlier, think back in 5500. But there's something called a backward elimination process. And the first time I saw backward elimination was actually when I started studying multiple regression. It's a procedure that's used a lot, but it's not really one that I prefer. Backward elimination is typically a process that puts information into a computer, and then a computer does the thinking for you. I tend to prefer statistical analyses that are, or at least studies that are more theoretically driven and, you know, I guess creatively driven than letting a computer do that kind of work for you. But what happens with a backward elimination is you begin with your entire model, and I'll illustrate that in just a second with multiple regression. So in the term of the loglinear model, we'll start with the most complicated model, hence, you know, with no error, the saturated model. And I think you see where this is headed. We're going to start with a model and start taking bits and pieces out of it, contingent upon certain constraints and certain measurements. Now, guys, what happens in let's take a look at this with multiple regression, and let's say that we have created a model that I don't know. Let's just keep it really simple here. And we have a 4 predictor model, well, 4 predictor model, you know, with the intercept. And what we would do if we started the backward elimination is we would, in some statistical software package, we would hit backward elimination, and it would go through all of the coefficients, and it would find the coefficient with the highest p-value. And let's just say, for example, it's B3. It would eliminate this and compare the changes in the R squared. So the first model, we can say, includes B1, B2, B3, and B4. And essentially it has an R squared. The second model would include B1, B2, and B4, and it would also include an R squared. Okay, what the statistical, what the program would do, R in this case, it will compare the change in the R squareds. If these R squareds aren't, if the change is non-significant, then it will conclude that B3 really doesn't add a lot of value to our model. So we can use B1, B2, and B4 equally as successful in predicting Y as if B3 is included. Now, if this change turns out to be statistically significant, then we're saying that eliminating B3 causes, well, B3 should be included in our model because it has the change in R square, because this R square is gonna decrease when we take out predictors. So that's a process that we use in multiple regression a lot, or others use in multiple regression a lot, and it's something that's going to play a role in this log linear analysis that we're probably either going to get to in this video or start in the next video. Well, guys, we're going to use the same process with a few tricks to run a log linear analysis. Now, the steps here, for the backward, get it down where you can see it, for the backward elimination, go as follows. And this is just more in general. The first thing we do is we begin with the saturated model. And guys, this is just, we begin with the full model. The next thing we do is we're going to remove the predictor, not randomly. Remove a predictor with the highest order interaction. The third thing we're going to do is we're going to compare these log likelihood chi-square test statistic. So we're going to have the log likelihood chi-square statistic from the previous model. And we're going to have a new one for the current model. And guys, we're just going to compare those. And if the change in those is statistically significant, then we can see that removal of that highest order interaction causes you know, a drastic change in our model. Now, so guys, at the end of the day, we'll examine the effect of removing the highest order interaction and reevaluate the model. If the new fit isn't much different than the old fit, then we could reasonably argue that the interaction isn't needed to appropriately describe the relationship. Keep in mind, however, once we begin the removal of terms and we leave the saturated model, then of course we're going to bring error into our calculations. All right, so I think you should have a pretty clear understanding of where we're actually headed with this, okay? So let's kind of start to get our hands dirty a little bit. Let's examine, or at least set the stage for this situation. So I want to look at political party. And clearly that's across Democrat or Republican. The next thing I'd like to look at is belief. And this is either life versus choice. And then I'd like to enter in another obvious categorical variable that we may be interested in the context of a problem like this. And that would be gender. Okay. Now guys, from this we're going to have three two-way interactions. You're going to have party across belief, party across gender, and you're going to have belief across gender. Because we're obviously going to have one three-way interaction. And that will be the three-way interaction of party across belief across gender. Guys, revisiting the steps with much more focus on this problem. What we'll intend to do is again, start with this full model. eliminate, the interaction with the highest order. So in this, it's going to be the party over the belief over the gender. All right, we're going to calculate the likelihood ratio statistic. So guys, remember from a previous video that the likelihood ratio statistic was, what was it? It's 2 times. I didn't think I'd even need this. What is it? The observed JK times, and okay, here we go. To use this, okay? So that will be calculated. The third thing we're going to do is we're going to sit back and see what happens. So, and one of two things is going to occur here. Either the change in this value will be statistically significant or not statistically significant. Now, what do we do in these situations? Guys, if the change is statistically significant, then we can say that the removal has a significant effect on the full model, so it's important and should be left in, should be examined. If we have a situation where the change is not statistically significant, then it can be argued that the removal has no effect, so it can be removed. Again, it kind of goes back to something I've always heard in policy studies, that if 2 people always agree, then one of them isn't needed. Because, again, essentially they contain the same information. So if we get in a situation where we have not statistically significant, then, again, the removal has no effect on the overall model, so really there's no need keeping it involved, keeping it included, I should say. Okay, so back to log linear analysis. If the highest order, again, is statistically significant, then we stop. And all lower order interactions are built into the higher level interaction. So we examine in this case, the 3-way interaction. Otherwise, let's say that we examine the interaction of our 3 variables, A, B, and C. And let's say that this is not statistically significant. Then what we're going to do is we're going to examine the 3 two-way interactions and see how they impact the model. From there, if all 2-way interactions are not significant, then we move to the main effect. If either, any, or all of the 2-way interactions are statistically significant, we don't move on to the main effects for the same reason, the same argument that we had before, that the information in the main effects is included somewhere in one of these 2-way effects. So guys, at the end of the day, our test statistic is going to be the likelihood of chi-square, and we're going to call this of the change. And this is easily calculated by taking the test statistic for the current model. Guys, the current model is going to be the one that's going to have the interaction removed. And we'll look at the test statistic from the previous. All right. I really seriously considered showing the calculations for this because I think there would be some value in it. Let's see how far we get in this video and see how much we get into next week or I should say the next couple of videos when we illustrate this. And this is just getting annoying as can be, guys. There we go. There's a textbook that I have that gives an excellent illustration of the calculations, and I really want to show that to you, and share it with you if there's enough time. So, guys, you know what happens just about with any new statistical technique that we are introduced to. We need to understand the statistical assumptions and the underlying assumptions. So the first thing we always need is independence. And guys, at the end of the day, independence here just says that each entity falls in only one cell. So subject number 1 is a female Republican who is pro-choice. Subject number 2 is a male who is a Democrat and believes equally of pro-life, pro-choice. This person needs to be removed from our analysis. They have to fall into some entity or into a distinct cell. The second thing that we have to talk about is the expected cell count must be large enough. Notice intentionally softer language here. When we're in a 2x2 situation, and we used chi-square in the previous videos, our threshold was 5, well, bigger than 5. Got a little bit more flexibility when we have 3 or more. So, you know, get this in your notes and write this down. The things we need here is we definitely need the expected cell counts to be greater than 1. And all the resources that I've seen says that up to 20% of the cells may be below 5. Now, guys, remember in the 2x2 situation, we couldn't have any cells below 5. So, in our situation where we have 2 parties and 2 gender and 2 beliefs, then we have 8 cells, right? And times 20% is 1.6. Well, we can't have any more than 1.6, which tells us that we would be allowed 1 cell that could be below 5. And again, it can't be below 1. It could be below 5, but all of them need to be greater than 1. So these kinds of things, you know, when you do your final project, these are the kinds of things that you're going to need to revisit. Guys, while we're on a roll, it's looking more and more like I'm not going to get to all the calculations in this video, but we'll see what happens. Remedies for low cell count. Number 1, collect more data. That is always a way to approach a situation like this. What happens when we get into cell counts, expected cell counts that are too low, is we lose power. So, you know, again, loss of power just means that we don't have sufficient chance of rejecting a false null. So another kind of naive remedy is just accept the fact and report that you have low power. I think this is kind of lame, especially if you're trying to get something published in a refereed journal. It would be something that we wouldn't allow, that I wouldn't allow in your master's thesis, to be able to just accept that. We need to do something about it. Third thing, probably this is by far the most preferred way of approaching this is collapse your variables. And what I would mean there is, let's just say that we had a political party and we had moderate and Democrat and Republican and independent and libertarian. I think that's spelled right, yeah. Okay, and we run into a situation where we don't have sufficient expected cell count. What I would probably do is I would assign these in ways that make sense. Pretend that goes over there, and put that as other. You want to combine these things, things that make sense. You don't want to just like flip a coin and just arbitrarily start putting stuff together. So now, one thing I want to warn you about, and I'll give you the opportunity to screw this up in your assignment, so I'll actually find out whether you watched this part of the video, or I may, I don't know. Slightly tricky, and it really depends on who you listen to. If you collapse a variable, a couple of things you got to take into account here. First of all, the highest order interaction must be non-significant. Moreover, at least one lower order interaction must be non-significant. Okay, so that's just one of those things that that you got to check out when you're making things happen. If you're going to collapse things, collapse a variable. Guys, I say we get our hands dirty here and go work a problem and see how far we can get. Looks like I'm into this video a little longer than what I'd hoped to be. So let's open up R, and let me show you what I've done. I've uploaded a data set to Blackboard, and that data set is called Party Belief Gender. So what I want to do here is I want to bring up R and do some stuff that we've done before. First thing I need to do is, just like we've done previously, set the working directory. And then I want to go get my data. So what did I say? Party belief gender.csv. Don't forget to attach your data. And we can type in names data, and we can see that the way that the variables are presented. Now I want to go ahead just do this. You notice we have 880. These things aren't coded in zeros and ones like previous data sets. They're actually reported as dim and REP and then male, female, and choice. Yeah, you got to pay attention to the capitalization because that can make a difference. So again, I want to have these handy. Now, guys, previously we used the cross table function, and I think we need to, if you remember, we've got to access the shoot, I forget what it was. What was the name of the shoot? Was it G models? Yeah. So we have to access G models to make this cross table function work, but we have to. It won't work in the case where we have three variables. So we've got to modify it using what we call the subset command. So the first thing we need to do is we need to create two new data frames based on dichotomizing one of the variables. Well, since we've worked previously with the Republican and or the party in belief, we're bringing in the gender variable. So I want to use it to create two data frames. Okay. So I'm going to do this. I'm just going to create, I'm just going to call this kind of strangely just males. So I want to create one data frame where I can look at my data set just over males and another one just over females. And it's kind of cool the way we do this. Just there's a subset function and just tell, what data set it wants to, we want to kind of partition this into. And then I want gender to be equal to male. And then I want to do just females. And I want to do subset data gender equal to female. Let me make sure that I didn't use female as a capital F. Okay, cool. Don't know why I checked it because it definitely would have let me know, right? Now, what I'd like to do is use the cross table like I did before. And here what I want to do is I want to do just males, $ over party, just males, $ over belief. So what this is going to do, it's going to give me a 2x2 contingency table for party over belief, but it's going to look just at males. And this is going to be beneficial for some things we want to do later. I really don't care about the chi-square and the odds ratio that we looked at before. But you know what? Something that may come in handy are these standardized residuals. Yeah. Now, guys, when I look at this, I don't know why it didn't include that. Oh, I do know why I didn't include it too. We got to come in the end and do format equal SPSS. I don't know why, but chi-square contribution doesn't seem like it gave us the standardized residuals. Well, guys, I gotta tell you, I don't understand. Maybe it's maybe something's going on with this. Oh, I see what it is. Standardized residuals. Okay, why is this not working? Because I'm having a bozo moment right here. Yes, we said true. This this should work. Okay. I completely just lost my mind on that entry right there. I don't know why I used the other. That should just be SRESID. Now, when I look at this, you know, there's a lot of things that interest me here, and a lot of things, you know, if this was something that we collected and really cared about. But I have a tendency to examine the standardized residual first, see if we have anything above 2 or below -2. In this situation, just for males, you can see that all of our standardized residuals are above 2 or below -2. The highest one is this one right here, 6.1, and this tells us that the observed cell count for a Republican male who is pro-life is 6.1 standard errors higher than we would have expected it to be under the null hypothesis, which says that the two aren't related. The two variables aren't related. So I think that's kind of interesting to look at. Next thing I'd want to do is go up and I want to look at just females. And again, I have a tendency to look at the standardized residuals, and it turns out that they're all above 2 or below -2. And again, it seems like the Republican life component for females and males seems to have the highest absolute value standardized residuals. So guys, it's these. You know, this is pretty much what we've done before. What we're going to do, there's a function that we'll run into in the next video. I think I've got too much going on here. It's called the log linear model, and we're gonna learn to use that and see what's going on with this party, belief, and gender situation that for the status set that I've mostly just made up. So guys, I don't have enough room on this one to go much further, so pretty easy video. So we'll call it a day. Take care.